Greetings. Welcome to video number 9 in Data Science Dojo's series on Introduction to Text Analytics with R. I am your host, Dave Langer. What I have here is an RStudio environment with all the code through video number 8 executed. And as you recall from at the end of video 8, we were discussing some of the output from the awesome confusion matrix function. As a refresher, don't hesitate to use the help system here. Confusion matrix, create a confusion matrix. Now, in particular, what we talked about was that the confusion matrix function from caret not only produced a confusion matrix, which is this table of numbers right here, and provided you with an accuracy number, but it also provided you with a bunch of other metrics that would be useful. And the focus of today's video is going to be drilling on these first two highlighted metrics, sensitivity and specificity, particularly in the context of when you're doing applied data science in the real world. Accuracy is obviously a very common metric that is used. It's very intuitive and people understand it, but it's not always necessarily the best metric to use. And it may be beneficial for you to either change your metric from accuracy to something else as your major KPI, or alternatively, you still keep accuracy as your major KPI, but you also use other metrics as well to help guide you in your efforts for building the most effective machine learning models. And the example that we used last time, which bears repeating, is that you can make an argument that in a spam filter case, a spam detection case, that there are two scenarios that can occur, two bad scenarios that can occur, and one is probably worse from a business perspective than the other. And as a refresher, one of those scenarios is I have spam, right? I have a bad email, an illegitimate text message, what have you, that comes in, and we incorrectly predict with our model that in fact it's legitimate. So even though it's spam, we say it's ham, and it falls through. It flows through to the user. That's not ideal, but arguably is not as bad as the alternative, which is we have a good piece of email, a good SMS message, a good Twitter, whatever, a tweet, whatever. But in fact, we erroneously predict or we erroneously classify with our machine learning model that in fact it's spam, it's illegitimate, and maybe put it in a separate folder or in a separate part of our application. That is arguably worse. It's arguable that our users will tend to forgive us from occasionally thinking that spam is actually legit, rather than on a fairly regular basis incorrectly taking their legitimate messages and thinking that they're bad and then put them like in a spam folder where maybe they missed them. So using accuracy isn't going to necessarily get you where you want to be. Other metrics can hone in, for example, on how well you're doing for classifying spam, how well you're doing for classifying ham, and you can use those in conjunction with accuracy to actually gauge whether or not your models are actually improving in the way that the business needs, or if your feature engineering efforts are producing the results that the business needs. Okay, so what we'll do is we'll actually pop over into some slides and talk a little bit more about sensitivity and specificity and how we can use those to help us build a more effective spam predictor model. Okay, so here we have in our PowerPoint a representation of a confusion matrix which matches what we saw in the R command line output. Our columns here, ham and spam, are our references, or the actual labels. In fact, these are the hams, and in fact, these are the spams. In the rows are our predictions. Our model predicted ham, our model predicted spam. Now, where these intersect, we now have 4 quadrants, A, B, C, and D. Now, if you're familiar with statistics at all, you will immediately recognize that these are in fact mapped to the ideas of true positive, right? It was ham, and I predicted ham, so true positive. False positive, it was spam, but in fact I predicted ham. That's a false positive. False negatives, it was in fact ham, but I predicted spam. And then lastly, the true negative. The message was spam, and I predicted spam. Now this will be important because as we talk about accuracy, sensitivity, and specificity, we'll use these terms. We'll use the quadrant letters as well as TP, FP, FN, and TN, as well as part of our mathematical definitions. But the thing to remember is the stuff that I get correct is along this diagonal from the top left to the bottom right. This is the stuff I get correct. The stuff I get wrong is the opposite diagonal. Okay. So first up on the hit parade, accuracy. Now you'll notice that I just added the TP and the FP and the FN and the TN here, but otherwise this table is exactly as the one that we saw previously. So I like to think, when I talk about metrics, when I teach metrics to our bootcamp students, I like to talk about the intuition. What is the metric trying to tell you? What is the metric helpful for? What kind of questions does the metric answer? They usually put these different kinds of metrics in a very intuitive light, and then you can start to think about how they work, which ones will be appropriate for your business situation, so on and so forth. So I know this will be exceedingly simple because everyone knows what accuracy is, but it just go with me for a second here. Okay. So the intuition of accuracy is simple. What percentage of the predictions were correct? That's all it is. I made some predictions. My model made some predictions. What percentage of all the predictions were actually correct? So mathematically, accuracy can be formulated this way. It's a ratio. Most metrics are ratios, obviously. So accuracy is no different. So if we actually take this apart and just take a look at the numerator and the denominator, the first thing we can see is that the numerator of accuracy is essentially the diagonal, which is, I said earlier on the previous slide, the diagonal from the top left to the bottom right is what we get right. That's what it is. So the top part is what we get right. The bottom part is basically everything. So intuitively enough, accuracy is simply just the ratio of the things I get correct vis-a-vis all of the predictions that I make. The predictions I get correct divided by all my predictions. That's the accuracy. It's your percentage. Very intuitive. But as we've seen, accuracy alone may not necessarily be enough, because I'm actually maybe more interested in ensuring that I get ham correctly predicted more than I'm interested in getting spam correctly predicted, because my customers may be more forgiving of spam errors versus ham errors. So moving on, we can look at sensitivity. Now here's the intuition around sensitivity. Sensitivity is what percentage of my ham messages were correctly predicted. Not what percentage of all the predictions were correct, just only the ham messages. I don't care about spam for this particular metric. I only care about ham. Out of all of the ham predictions that I made, what percentage of those predictions were correct? And there's the math. Not surprisingly, we'll go ahead and decompose it just like we did before. So our numerator is the true positive, right? Of the ham messages, how many did I actually predict were ham? That's A, the green box. Versus the total number of ham predictions I made altogether, both correct and incorrect. Now, obviously, sensitivity is going to be a good metric for us to pay attention to, under the assumption that we would prefer in general to make mistakes on the spam side of the house rather than on the ham side of the house, because our customers are likely to be more forgiving in those kinds of mistakes. Now, if you're in the business world, you can think of any number of situations where this idea is going to be true, especially in the binary case, because they're replete in the business world, where you can say, look, you know what? If I had to make an error one way or the other from a business perspective, I would rather make this kind of error because it's less costly, it generates more revenue, it has less customer dissatisfaction, you name it, right? So there are all kinds of examples of this. So sensitivity is a very, very good metric to use in those types of situations. Now, surprisingly, if there's one for ham, if there's a metric for ham, there's also going to be a metric for spam. And in fact, there is. This is called specificity. And the intuition here would be exactly the opposite of what we saw on the previous slide. What percentage of the spam messages were correctly predicted? And once again, the math is not too terribly difficult, as you might imagine. It's just Tn over Fp plus Tn. Or if we decompose it again with our little colored boxes, the numerator is how many of the spam messages did I in fact correctly predict, divided by the total number of spam predictions that I made. And that gives me the relative percentage. Now here's the thing. And this is one of the things that makes data science both a lot of fun and frustrating at the same time, which is you can create lots of features. Feature engineering is super, super important in applied machine learning, applied data science. especially in business scenarios. You make new features, it allows the information to pop, it makes the machine learning algorithms work a lot better. However, most of the time what you'll end up finding is that your features either don't work, and that's totally normal, by the way. You have to go through a lot of features to find the nuggets of gold. Or they work but they have unintended consequences. For example, and this is the reason why we're going through these metrics here. It is entirely possible for you to engineer a feature that increases your accuracy overall, but negatively impacts, for example, your sensitivity. Because if you go look at the metrics, what will happen is your accuracy will go up, your sensitivity could go down, but your specificity goes up at a higher rate than sensitivity is going down. Ergo, you get a net increase in accuracy. Now, maybe that's okay, but in our particular case, this hypothetical example wouldn't be so ideal because we prefer to have mistakes, if they exist anywhere, on the spam side of the house. So what we would tend to prefer as a result is if we had to choose, now obviously we'd like both to go up at the same time, both sensitivity and specificity to go up at the same time, but if they cannot, we would tend to prefer sensitivity to go up more than we would prefer specificity to go up, because we prefer being correct with the ham example, the ham scenario, than we do about the spam scenario. Okay. So there you have it. Quick and dirty coverage of metrics. Enough of the slideware. Let's go ahead and get back to R code. Okay, so we're back in R. And let's move on. So what we have here is a pretty good indication of what's going on. So we have our data. So we ran it through a pre-processing pipeline, lowercase, tokenized, removed stop words. We stemmed. We added bigrams in addition to our unigrams. We TF-IDF'd it. And then we projected it down using singular value decomposition, SVD, from 29,200 and something features down to 300 features. We built a mighty random forest, and this is what we got from the results of our cross-validation run. 96.82% accuracy, but notice that our sensitivity is 96.65, and our specificity is 0.9831. And based on the metrics, you would know that this essentially is, this value comes from dividing this number by this number plus this number, and this number comes from this number divided by this number and that number. And just to prove it to you, 406 divided by 413 gives you 98.3, or 0.983, sorry about that. There you go. So, not bad. But what we see here is that our model is actually better at predicting spam than it is ham, at least to start with. So ideally what we would like to do is engineer some features that not only increase our overall accuracy, obviously, because ideally we'd like to be 100% accurate, even though that's probably hard to do in practice. We'd like to increase our overall accuracy, but in general we would also like to see these sensitivity numbers coming up, because our core assumption again is that we prefer not to make mistakes in the sensitivity space if we can help it. Okay, so early on in the video series, we created a feature. If you recall, we created a feature called text length. And essentially this was just the count of the number of characters in the SMS text message. And we did a little ggplot2 action on that. And we found that in fact, it was actually looks to be a pretty good feature. Just based on inspection, it looks like it would actually be quite predictive potentially. So why don't we go ahead and add that into the mix? We can add a new feature to our train.svd data frame called text length. Just pack in the original data that we calculated on it. And now we have a new feature to augment our SVD features that we have for all the unigrams and bigrams. So if I run this line of code, I could then, of course, now redo my process, right? You know, our tenfold cross-validation repeated 3 times, with mighty random forests, with 500 trees apiece, tuned over 7 different values of mtry. Now, it'll take a while to run, and you'll need a pretty beefy machine to run it as currently coded. But as before, I've actually ran this already and cached the results in a binary file that's available from the GitHub. So if you get the files from the GitHub, there'll be one called rf.cv.2.rdata. You can load this up with the code and check out the results without having to wait 20, 40, 80 minutes to actually have the above code run. So let's go ahead and execute that. And here's what you can see. You can see that in this particular run, the best value for mtry was not 151 variables per tree, but 101 columns per tree. And you'll notice here that the accuracy was a little over 97%, which was higher than the previous example. But as we know, accuracy alone is not enough to understand what's going on. So let's drill down. Once again, let's use our confusion matrix function from caret and drill down on what's going on here. Now, first up, what you should notice is that our accuracy has gone up. It's gone up a little bit. But more importantly, look at our sensitivity and our specificity. Both of those numbers have gone up as well. Our specificity is approaching 100%, which means we are getting very, very close to being able to identify spam correctly, at least based on the training data, because notice we only get 3 wrong. Also notice that we did have a reduction in our ham errors. In the previous confusion matrix, if I go up here real quick, I'll show you. We had 117, so we actually were able to now correctly classify an additional 7 here. So we went from 117 wrong to 110 wrong, which gave us a little bit of a bump. So in general, this is a good feature. This is what we like to see. Our accuracy is going up, but also our sensitivity and our specificity are also rising at the same time. Now we got more bump in specificity. We got more increase in our ability to correctly classify spam than we did ham, but at least we got both going in the right direction. They're both going up. So this is a good feature. Now the reason why this is a good feature is that this is a good indication. It's only an indication, but it's a good indication that this feature may actually be useful in production against unseen data. And this is going to be super important because, as we'll see later in the series, towards the end of the series in particular, this is going to be super important because when we train our model, we're only going to have a certain number of n-grams to use because we'll only have the text messages at our disposal to use to build our training set. Now, as everyone is probably aware, people tend to use different types of words and use different types of styles, especially for social media communication, and it morphs pretty regularly over time, which means that your data is going to become stale pretty quickly. So ideally what you're looking for is features that actually capture, not to sound very, very flowery here, but capture the transcendent underlying truth of the data. So a feature that can, such as text length, that tends to not only increase accuracy but also increase sensitivity and specificity, that's a good indicator that it's possible that text length may be one of those transcendent universal truths in the data, that in general, spam, no matter what, tends to be longer than ham, because that's what we saw earlier. We won't know this for sure until we can confirm it in production or use our test holdout to confirm it, but in general, that's a good indicator. So these are exactly the kinds of features that you're looking for as a data scientist. Okay. That's great. Okay, but we're not done. So let's take a look at feature importance. So one aspect of the mighty random forest that is super, super cool is that as the algorithm runs, it can actually keep track of variable importance. If you actually go back up and you look at the code here that is commented out, I've actually specified that the random forest actually track importance. This is turned off by default, but you can ask the mighty random forest as it's training itself to say, look, keep track of what variables are actually important. Which ones are the most useful? Which ones are the most predictive? And it'll keep track of it for you. And then you can actually ask the mighty random forest later, hey, by the way, which features, which variables, which columns were actually important? Which ones were actually highly predictive? So we'll go ahead and take a look at that real quick. And then we'll end this video. So I need to load the random forest library first up. And then I can run the var implot function. And as always, never hesitate. Var implot. Variable importance plot. Interestingly enough. Now what I'm going to do is I'm actually going to do the first CV run. This is the run without text length, right? This is the first one we looked at. This is one that was 96%-ish accurate, just so you get some idea of what was going on with that particular model. So if I zoom in on that, you can see that, the variable that is x24 is by far and away the most important. You can see that way over here. It's by far and away the most important. And the next up was x159, x85. Now, as I promised in previous videos, what is x24? Oh, we don't know. We don't know, right? Because it's some sort of weird combination of one of those 29,200 something columns that the mathematics said was actually significant. But the main idea is to show you is that some features will tend to be very, very predictive, very, very significant, far over here on the right, far over here on the right. And then some will be less, right? For example, x57 is way down here. Notice how far apart it is. Okay, excellent. Next up, let's take a look at our new. Okay. Now you'll notice that the visualizations are a little bit different. Don't worry about that. Notice that this right-hand graph, this right-hand plot, was the same plot that we saw in the previous visualization. Okay. And notice this is super interesting, right? In our first plot, x24 was by far and away the most important. But notice that text length has essentially squished all of these features down. So what's the interpretation? As a data scientist, what should you think about this? And the answer, in very simple terms, is that text length is by far and away a better feature than any individual column that we were able to extract out using latent semantic analysis. That is, our singular value decomposition, our matrix factorization that tried to extract as much info as they could out of those TF-IDF unigram and bigram columns weren't nearly as powerful. There isn't one that is nearly as good as the text length. And that actually happens quite a bit in text analytics. Generally speaking, individual word features most of the time tend to be relatively weak. And the features that you can engineer as a data scientist will often be far stronger. And that's really where you make your money as a data scientist, right? If you could just get away with just, you know what, I'm going to create my standard pipeline, I'm going to go ahead and TF-IDF it, I'm going to go ahead and SVD it, and that gets me all the way, home, 99% of the time, then the data scientist position wouldn't be one of the best jobs in the world because it would be commoditized and automated, right? It's this idea here. And I mean, it's a very simple feature, to be sure. Don't get me wrong. I mean, this is not genius, by the way, but I'm just using it as an example, an example of saying this is where you add value as a data scientist is feature engineering, because you get this. If you create good features like this, they will typically be disproportionately powerful, disproportionately useful in a text analytics scenario. And that's where you make your money as a data scientist. Okay, I'm going to go ahead and stop there for this video. In the next video, we will actually take this idea of feature engineering a little bit further. We'll use cosine similarity and engineer a new feature and add it in and see how it works. And so hopefully you'll be excited for seeing that. And that video will be coming up 1 week after this video gets published to the YouTube channel. So if you like what we're doing here, if you like this video series, if you like our YouTube tutorials in general, please subscribe to the Data Science Dojo YouTube channel. We'll be producing content on a weekly basis. Also, if you like what we're doing at Data Science Dojo more generally, we do have various social media feeds on Twitter, LinkedIn, Facebook, etc. You can go ahead and subscribe to those, and you'll get a font of curated data science goodness if you're interested in learning more about what's going on in the world of data science. Also, if you are so inclined, we do teach a 5-day intensive data science boot camp. So if you're interested in bootstrapping into some new foundational data science skills, and you don't necessarily have the ability to take 12 weeks off of work to do that, you should probably check out our website at datasciencedojo.com. Okay, this is Dave Langer signing off, and I wish you very happy data sleuthing.